and also Wednesday, or Tuesday and also Wednesday, is statics. That is figuring out the forces on objects that are not moving. The big application here is civil engineering. What are the forces on a bridge? What are the forces on a road?
Are you talking about cars going over top?
With or without cars going over the top? Yep.
So just like based on the weight, then not the ground.
Mr. Cable, should me and Eric do the quiz now or wait?
That's a good point. Let me go ahead and print out the quizzes for you. Okay, we're back. So, as a for instance, I want you to imagine that we have a seesaw. When was the last time you were on a seesaw?
2 years ago.
2 years ago. Summer?
Senior picnic. It was
Senior
awesome.
picnic. Awesome.
We got it balanced.
And the way a seesaw works is pretty simple. You have a fulcrum in the center, and the fulcrum is a pivot point. And what you do is you stick people on it so that it ends up balancing. Now let's do a for instance here. Let's imagine that we have Alex on one end. What's your mass in kilograms? 1 kilogram is 2.2 pounds.
Thank you.
Alright, I'll say
What's that?
like I'll say 70.
70 kilograms.
No, 70.2.
Divide by 2.2, you shave that down a little bit, so you go with like 65. Alright, so we're going to put Alex on here at 65 kilograms. We're going to put him 1 foot from the end of the seesaw, which is going to have a length, total length of 8 feet. Now on the other end, we're going to put the entire 6th grade class. No, I'm kidding. We're going to put somebody bigger.
Or lighter.
I'll do it.
Let's say 150 kilograms, 330 pounds. And so the question is, where do we put this individual?
Like one of those big old TVs that have like the
Really, really close.
My grandparents had one of those.
Like he needs to be like on the very, very edge.
No. Really, really close. To
That's what I meant.
Not,
That's what I meant.
not the edge off the line.
You know what I meant.
So where can we put this 150 kilogram person so that the whole thing will balance? Now, interestingly, this question admits of several different similar solutions that are all kind of related to one another. One way that I could think about it is in terms of inverse proportions, because the 60 kilogram mass times its moment around the fulcrum, that would be its distance right here, times 3 feet. The total quantity here is called the moment of the 60 kilogram about the fulcrum. Has to equal or balance out the 150 kilograms times our unknown distance x from the fulcrum. So this would be one fairly simple solution here, in which we find out that x is equal to 65 over 30, which is going to be 2.2 feet from the fulcrum. In other words, this guy has to go to a distance of 2.2 in order to balance out this guy at a distance of 3. Did I do the math right on that? That seems wrong.
The guy.
65 over 50, thank you. So it's actually 1.3 feet. Much better. So that 65 times 3 is equal to 150 times 1.3. That's much better. Yep. So that's one way that we could approach this problem. A second way we could approach it is by using the concept of center of mass, right? If we put an origin on our system, let's say 0 right here, and we now give a distance, an unknown distance x to our 150 kilogram, then what we would like for to happen is for the center of mass to be located right at the fulcrum, which is at 4 feet. And so we can set that up as the center of mass is the sum of mass times position divided by the total mass, which is going to be equal to 65 times 1 plus 150 times x, all of that divided by the total mass, which is 215 kilograms, and that has to equal 4 feet. And so if we solve for x, we now get 65 plus 150x is equal to 860, or in other words, 150 is equal to 695. And then we get x is equal to 695 over 150, whatever that may be. $695 divided by 150 gives me 4.6 right here. Now you say, how come this answer is different from the one that we got previously?
4.6 from the left side.
It's 4.6 from the left side, but even there, it's still giving us a slightly different result. I wonder if I screwed something up.
It's like half of
I should get exactly the same location.
Except that's exactly half of the first one. It's 1.3 divided by 2.
Huh. That's interesting. This worked out fine in the other class.
Wait, scroll down.
No.
That's really pretty strange. Let's try this first calculation again. 65 times 3 divided by 150 is 1.3. Yeah, that's right. Yeah. We are having strange technical difficulties here. Total mass is 215, right? Yep. Minus the 65. Oh, 795. There you go. Divided by 150 is 5.3. There you go. Much better. We apologize for the arithmetic unit failure. And this gives us 5.3 feet. And so we say, well, why is this a different number? And it's because it's measured from the left edge. So we actually get the same physical location, but specified with a different coordinate. So these are a couple of ways that we could solve this problem, but today I'd like to introduce you to a more general method that will allow us to solve a much larger class of problems, and that is sum of forces, sum of torques. So this is our big method for today. And I remind you of Newton's first law, which is that the sum of forces on an object is equal to 0 if and only if the acceleration is 0. And in particular, what this means is if my object is not moving, then it's the sum of forces on it must necessarily be 0. Peter. Yes.
So would any forces acting on an electron be negligible so the mass is so small?
They're going to be really small. Yeah. Even a small force acting on an electron will whip it around.
Yeah, no, but would that be like would it make the force?
So like if you calculate for a hydrogen atom and you pretend that the electron is just orbiting around it, and when you do the calculations you find out that the acceleration of the electron is 10 to the 14th meters per second squared.
So it balances out.
It's a huge acceleration. But the mass of the electron is 10 to the minus 31st, so that the force acting on it is about 10 to the minus 17th meters.
It's like almost negligible.
That's negative, yeah. And that's the electrostatic attraction. The gravitational force on it is 10 to the minus 30th newtons. So we've just given more gravity.
So if it doesn't hit into anything else, which is impossible, so it only have to be like 1/11, but if it didn't hit into anything else, what would be like the maximum speed that the electron would reach? Because it wouldn't encounter much air resistance. Or any air resistance, I guess.
Again, pretending that the electron is just going in a circle around the atom, which it isn't really.
Okay.
Then I believe the speeds that you end up calculating are on the order of 10 to the 6 meters per second. So 100th of the speed of light. I think that's about right.
1.85 more going up now.
So now, coming back to our story here, let's extend this a little bit. Because sum of torques or net torque equals I alpha, if the alpha is 0, then the sum of torques necessarily is also. And so this means that the sum of torques around any point will be 0 if and only if the object's angular acceleration is 0 also. We're going to utilize these two facts to solve every single problem in this chapter. Yes?
Okay, one other question. This is off topic, but if you were to, like, let's say someone was standing about 3 feet in front of you, and they threw a football ball at, like, whatever speed you said before, like, ridiculously fast, and it hit you. Would that actually be enough to, like, knock you back, or would the foam still be enough to break you?
Well, as it turns out, if they were somehow able to throw it that fast, then as it hit you, the football would begin to vaporize. And so would you. So you ended up with a very large hole. That's really what would happen.
That's so we have the relatives.
Yeah. So yes, there would be momentum.
But wait,
But
why?
most of that momentum would be carried off by the particles of your abdomen exploding
Alexis,
around beyond you.
a fastball hits you with a glove off, would you get it hurts, right?
No, I don't know. I don't.
In football?
Okay. Coming back to our story here. We have our two objects, like so, and we have our seesaw, like so, and we have our fulcrum, like so. And the way in which we're going to analyze this is by means of a free body diagram. To analyze the forces that are on. And as we put forces on our free body diagram, we're going to pay attention to direction as much as possible. What's the force from this guy? What's the force from that guy?
1,500
1,500
Newton.
newtons. And let's not forget also the force from the fulcrum, which we're going to call F. Okay. And in addition to the forces, we're also going to put distances. Now you can pick a point, any point, but I usually pick the left end. So this guy is at a 1 meter distance. The force of the fulcrum is at a I said meter, it's foot, isn't it? In the original problem. At a 1 foot distance. This is at a 4 foot distance. And the force here is at an unknown distance, which we shall call x.
Oh, you're
Yep. So we're solving the same problem a couple of different ways here. All right?
I thought we were going to be speaking from that. That's very good.
So now what can I do with this? Now that I've got my free body diagram, I'm going to appeal to Newton's first law, either in the translational or in the rotational sense. If I do sum of forces, I'm going to march down the free body diagram and count up all my arrows, counting the downward pointing ones as negative and the upward pointing ones as positive. So we have negative 650 newtons, we have negative 1,500 newtons, and we have positive F. And all that equals 0. So that we can immediately figure out the value of F as 2150 newtons. Or in other words, the fulcrum has to support the combined weight of both people. Oh, that makes a whole lot of sense, doesn't it? And we expected that.
And that's based on the assumption that whatever they're sitting on was absolutely nothing.
Yes, that's right. The board is going to be of negligible mass for this problem. We'll work a problem in just a minute where that's not the case. But we still haven't found the value of x. So to do that, we're going to choose a point of rotation. Now, at first you might think the best point of rotation would be the fulcrum, and that's not a bad point of rotation. But if you think about it, in order for the seesaw to be balanced, then the rotation around any point has to be zero, right? So I might as well choose the most convenient point possible, and for me, because of the way I've labeled the distances, the left end is the most convenient point possible. You might think a different point is more convenient for you. Go for it. There is no wrong point to choose here. Some are easier, some are harder. If you choose a point in Peoria, you're going to have a hard time. So I'm going to choose this point right here, and I'm going to label it A, and I'm now going to go about computing the torques about point A. And I'm going to use the standard convention that any torque that is a counterclockwise torque is positive, any torque that is a clockwise torque will be negative. So I go to point A, and I start walking down these forces right here. 650 newtons times the distance, 1 foot, times the sine of the angle between. The angle between the force and the distance is 90 degrees, and the sine of 90 degrees is 1, so is therefore invisible. But now I ask, clockwise or counterclockwise? So I peg my finger right here at A, and I ask if this force has its way, will it do a clockwise or counterclockwise rotation?
Counter. Want to be the other way?
This force right here is pushing
Down.
rotationally, that way, which is clockwise.
So it would fall this way.
Huh? No, A is fixed.
Oh.
We're fixing A and letting the force have its way.
So it's not about the point of the fulcrum.
Well, technically it won't go
It's
down at all
around the
because-
point of the fulcrum.
Technically it won't go down because the fulcrum would be pushing up the equal force.
No, we're isolating just this point and this force. We're ignoring all of that. It's one at a time. We're not asking about the combined effect. And so because that force is causing a clockwise rotation, we give that a minus sign for its torque. Then we go to the fulcrum force. We already know the value of the fulcrum force. It is not 0. It is 2150. Yep. And it is operating at a 4-foot distance, and if I peg my finger right here at A, that F is rotating counterclockwise. So that we have plus F times 4 feet, which is the same as 2150 times 4 feet. And finally, we go out to the 1500 feet, and it is operating at a distance of X, and it is rotating which way? Clockwise or counter? Clockwise. Clockwise.
I did think of a clock. Oh.
Think if your numbers are getting bigger. So this is going from 3 o'clock to 6 o'clock, right? That's clockwise. And all of these torques now add up to 0. So this is negative 650 Newton feet plus 2150 times 4 is 8,600 Newton feet minus 1,500 newtons times x, and all of that equals 0. So we do a quick calculation. 8,600 minus 650 divided by 1,500, and lo and behold, we get the same 5.3 feet that we did in the other.
Where did you get the 8,600 from?
We have F times 4 feet, and we already found that F was 2150.
Oh, okay.
So 8,600.
So why didn't we replace F?
We could have.
I was just wondering if that makes sense.
No, I'm just trying to make it clear with respect to the diagram. Does this process make sense to everybody? How we're going about this?
It's some of the forces.
It's some of forces and some of torques. That's it. Yeah.
So can you do the same thing on like an object that's all curvy and stuff, like where they aren't like you can't just tell the distance by like 1 feet here and then tell a
Yep.
straight line.
And that's what the sine theta factor is all about for the torque. Yep. Now, let's actually take a look at a couple problems and see how this works out in practice. I want to take a look at problem number 6. What we have in problem number 6 is a diver who's standing on a diving board. And the diver has a mass of 68 kilograms, 58 kilograms. And she's standing on a board that has 2 supports. One's here and one's here. The distance here is 1 meter. And the distance here is 3 meters. And so what they want to know now, they label this point as A, and they label this point as B. What they want to know is, what are the forces FA and FB that are exerted by the 2 supports? Okay? So, where do I start? Good man. All right, and what forces show up here? Well, clearly, I have the 580 newtons. And also clearly, I'm going to have the forces FA and FB. How do I draw those?
Arrows.
Which way do they point?
Up.
Okay. FB. And FA. And we also need some distances. So we're going to have 1 meter from the end for this guy. And what's my distance for the 580 newtons? 4 meters. Exactly. Now we wonder about the weight of the board. Do we care about the weight of the board? Well, in part A, they tell us to not care about the weight of the board. And in part B, they give us a mass of the board and tell us to care about the weight. So we'll do part A first. In part A, the weight of the board is 0. Okay. And now we're going to find FA and FB. All right, fair enough. So how do I begin? What's that? Sum of torques, okay. To do that, we need to pick a point of rotation.
It would be at the end on the left. I mean, at the end of the board on the left.
On the left, okay, that works.
Here, yeah.
There was no wrong answer for this, but this was a particularly good choice, and you'll see why. So if I now go through and I compute sum of torques about point A, then what do I get? That's not a sum of torques. That's a sum of forces. You gotta be clear on something. Forces are forces measured in newtons. Torques are forces times distances measured in newton meters.
So then we do FA times 1 meter?
Ah,
No, FA is 0.
FA times 0 meters because the point of rotation is the point of application of FA. And this is the first important problem-solving tip we learn in these, and that is that if you choose a point of rotation that is at the point of application of a force, the torque exerted by that force will be 0, and that force will drop out of our equation. This is very good. Keep going, Ben.
And plus FB times 1, or just FB?
Is that plus or minus?
Minus? Oh, is it clockwise?
Which one?
It's
Minus.
counter.
How do you know?
Andrew's whispering.
Yeah, don't let him whisper
No,
in your ear.
isn't it counterclockwise positive?
Counterclockwise is positive.
So it's counter.
Counterclockwise, why is it? Then fix your mental finger right at the point of rotation and let this force have its way.
Okay, so it's counterclockwise.
Counterclockwise. All right, keep going.
Minus
times 4 meters. And all of that now adds to 0, which gives us a really easy solution. FB is equal to 580 times 4 divided by 1, which is
2,023.20.
Yep, that's right. 202,320 newtons. That's a huge force for a 580 newton diagram. Why is that happening?
Because right now there's no support.
The distance.
It's so far away. Because of the distance.
But also, we're not counting the support beams.
If this reminds you of huge forces involved in supporting long robot arms at a long distance, then it should.
Easy.
Yep, exactly. All right, good. So that was very successful in finding the sum. In finding FB, we did the sum of torques around A. But I've only found one force. I need FA now.
Choose a different point.
I could choose a different point.
You choose both F and B.
Ah, let me choose point B and see what happens. So if I now do sum of torques around B, go. Alexis, this was your idea, so you get to do it.
Okay. FA is equal to 1.
I don't think you mean that. I think you mean FA times 1 meter.
Yes. That is what I mean. Plus FB times 0
Uh-huh.
minus 580 newtons times 4 meters.
And all that is 0. I'm happy with everything you did except for one thing. No, I'm happy. I'm actually unhappy.
Minus.
Negative.
Okay.
Yes, because this is a clockwise torque around this point. So please do not use up and down as your indicators for plus and minus. Please use clockwise and counterclockwise as your indicators for plus and minus. That's the first thing. Second thing I'm unhappy with is this distance right here.
3.
It's 3. It's the distance from B to the point of application of the force. Now I'm
about
happy.
the top one.
Now I'm happy. But then something happens that makes me mystified, and that is that when I solve for FA, I find out that FA is negative 1,740 newtons. What does
Because
this mean? Should I ignore the negative sign? No, it is telling me something legitimate. It's telling me that the way that I drew it on my diagram is the opposite of the way it is actually pointing. FA should have been drawn this way, and if I had drawn it this way, I would have ended up with a positive 1740, which is correct. Now, physically, why should FA be pulling down that way?
it's like a seesaw.
Yes, it's like a seesaw. If the diver is standing out here on the fulcrum, then the other support is actually going to have to be pulling downwards, dragging that board down in order to keep the diver from doing this.
But that isn't, well, it needs the support beam, but
Yes,
what would you say it was, it grabs it down, you said?
yes. It will be under stress or under tension.
So how would you calculate tension from?
You just did. It's a force. Yep. The stress would be calculated as the tension divided by the change in length. There will be a very small change in length for that thing. It will stretch under some length. Okay? So, a couple of interesting things about this. Now, what's very interesting is that none of you suggested doing sum of forces, and that actually saved us a little bit of effort. If I had done sum of forces to begin with, then I would have ended up with this equation, reading straight off of the diagram here. I would have gotten FA pointing up plus FB pointing up minus 580 newtons, and all that equals 0. This is a true equation, but what do you notice is slightly problematic about it? It has 2 variables. So it would have been less helpful than what you guys chose, which was to do sum of torques about A and sum of torques about B.
So
You
you're
can
trying
choose
to,
that.
Yeah.
are we smart
Andrew
enough?
tries it. Andrew tries it.
So the moral of the story is that you do not necessarily have to end up with multiple equations and multiple variables if you choose your points well.
Did the other class do something?
Yes, it is. I want to look at one more, which is number 11. and return to that, if you will. And in problem number 11, we have a ceiling and a wall, and we
Is this one
have
with the ball?
2 hooks with ropes that are connected like so, and a mass of, it was 170, I think. Yeah, 170 kilograms
That is.
hanging from this. Now, in the other class, they asked, why would anybody ever do this? And the answer might be that it might be the case that we had no choice about where the hooks are placed, and so we simply had to use the hooks that were already in the wall in order to tie the mass and support them. So the question that's posed now is, what will be the tension in the ropes? What are the tensions?
So you feel like that wall would have to be placed to go over the roughly.
Yes. You're not going to do this with drywall. Not even drywall with studs. Yeah, more like rip. It's going to be pretty exciting. Okay.
So I have the bookcase over my bed, and I'm always afraid that it will fall off the wall.
So with all our bookcases in our house, I find a stud, and I drill a hole through the back of the bookcase.
Oh, yeah.
And I put
Not
fire
a
extinguishers
bookcase,
in
it's
the
like
stud.
just a shelf. Imagine if I do stuff on it.
Oh, you're talking about the one above your couch?
Yeah, that should not. Okay, so let me pause this to tell a true story.
Yeah.
Our church used to be renting a building from somewhere else, and so the nursery was down in the basement. And on the wall was a shelf, and on the shelf was a speaker that people in the nursery would use to hear the sermon.
The speaker was a pizza baby.
Underneath the speaker, underneath that shelf was where the crib was.
That is not safe.
And my wife went to put Abigail in the crib when she was a little kid, and as she turned to do that, the speaker fell right into the crib.
Abigail wasn't in there, was it?
She was not wrong. She's alive, so no. She literally would have been killed.
That is quite the loss.
So let me strongly encourage you to move your stuff. All right. Now, the problem that we have is that we have 1, 2, 3 different ropes. If we only had one continuous rope, then we would say same rope, same tension, done. But we do not. So what are the tensions in these ropes? We're going to analyze this by choosing the knot where they come together as our object. And the reason that we do that is that this is where all 3 of these tensions come together, and therefore I can throw them into an equation. Let me number the ropes 1, 2, and 3, so that we have T1, T2, and T3 pulling downwards, or pulling off at the angle like that. And separately, we have the 170 kilogram mass that has its weight pulling down, and it has T2 pulling upwards. Please notice the little Newton's third law action right here. We've got an action-reaction pair on this rope. Everybody see that? Okay. Now, we're almost ready to go, but we notice one thing about our T3, and that is that it's pulling off at this funky angle. And so we say to ourselves, we need components for T3. We're going to take T3 and replace it with T3X and T3Y. And to do that, we need an angle, and look at that. This is a 33-degree angle right there. And we remember from Ms. John's geometry class that if you have parallel lines cut by a transversal, alternate interior angles are congruent, so that we have a 33-degree angle right here as well. So this component is going to be T3 cosine 33, and this component right here will be T3 sine 33. This is the only thing about this problem that was remotely tricky. So is everybody clear on this? And so now I'm ready to add up forces, and I'm going to add up forces in the x direction and in the y direction separately. In the x direction, I'm going to use only the horizontal arrows. So I have T1 pulling to the right, and I have T3 pulling, cosine 33 pulling to the left. Whereas in the y direction, I'm going to use only the vertical arrows, and I have T3 sine 33 going up. And I have T2, which is equal to 1700 newtons, pulling down. And that's an easy solve. That's right. Everybody find T3. Go.
I have a question. When I was like 6 months old, my dad was
You spell photo?
Isn't it, isn't it about
We only
3,400?
have a short amount of time. I'm sorry, to interrupt, but right after class.
Isn't it about 3,400? A little bit
Yeah.
over 3,400, about 3,450?
Other way.
Or down 30.
You should get this. Sine of 33 degrees, as he mentions, is close to 1/2. And so therefore, I believe you end up with 3150. Is that right?
3120.
3120. And now that I have this value right here, I can go back up to the original equation right there. And get T1 is equal to 3120 cosine 33, which is equal to just 20 something. You got it.
I don't know how to do sign. Like, it doesn't work. There's like a sign button and there's like a sign H button. It's just,
I wrote the sign button. The hyperbolic sign is not useful to us for this.
it's actually pretty.
Just like that.
With 20 degrees.
Now, we got this answer. The next question is, how do I check it? I'm working on a quiz or a test. I want to check it to see if it's right. How do I check it? Well, I'm going to check it by putting my values back into the diagram. Check by diagram. I'm going to put the T1, T2, and T3 that I have directly into the diagram. 3120. $26.17. No, this was $26.17, wasn't it? And this was $1,700. You say, well, how does that check it? Because when I put these into the diagram, they should add up as vectors to 0. Let's find out if they do. First of all, I need to split this guy into components so that this one is 3120 cosine 33. And when I compute that, lo and behold, it comes out to 26.17. And when I compute this guy, it should be 3120 times sine of 33, which is 1,700. And when I add them up, look at that, I get 0 in both directions. And so it checks out. If your diagram checks out, you did it right. The end. Should you check all your problems by putting them back into the diagram? Yes, you should. Why? Partly so that you know that you're right, and partly because you begin to understand the logic of these problems much more quickly if you're checking your answers by diagram. So check by diagram. It doesn't take long, and it really, really helps. Have a great week.